Let us now consider the Neumann problem and the mixed problem. And let us illustrate by using this Poisson equation, uxx plus uyy equal to this function fxy, which in this case, for simplicity, we choose this function to be equal to 12xy. In the example we are going to consider, we consider just a rectangle with side length 1.5 and 1. The x-axis is in this direction and here is the y direction, and the origin is here. We also assumed the following boundary conditions. On the left side we have u equal to 0, u equal to 0 on the bottom, and on the right hand side u is equal to 3 times the cube of y. So on these three sides we use just a Dirichlet condition, but on the top, on the other hand, we now use a Neumann condition. So here we assume that the normal derivative is equal to 6 times x. The normal derivative, since it points in the y direction, it will be identical with the partial derivative of u with respect to y. So we are going to, in our computation, we are going to use the approximation of this derivative, which we have shown you earlier. We will soon come back to this. Let us just recall the discretization equation for the Poisson problem. It is given by this equation. We also recall that uij is defined as the function or the value u of I h in the x coordinate and gh in the y coordinate. So in our example we have chosen h to be equal to 1/2. So h is the side length of these small squares. Since we know that u is equal to 3 times the cube of y, we are able to compute the values of u in these boundary points, in these green 3 boundary points. Here it is of course 0, because y is 0 at this point. Here we have 3 times the y value in this point is 1/2, is exactly the value of h, and we take the cube of this and we get 0.375. At this point we get 3 times 1, the cube of 1, which is 1 of course, and we get 3. U is equal to 3 in this point. We also use the same definition or notation for Fij. It's the same way of defining it as for u. And since we know that f is equal to 12 times x times y, we obtain that Fij is equal to, just put this value, this instead of x and this instead of y into this equation or the description of this function, and we obtain that this is equal to 3 times I times g. Okay, it's we have already shown you how to write this difference equation for the internal points. So for the point 1, 1, let's just show you these two equations, and for the point 2, 1, it looks like this. Here is the general difference equation, and we put I equal to 1 and G equal to 1. So then we get this equation. If we consider the next equation, the second point, 2, 1, we certainly get this equation. And we note that these are boundary points. This is the value of u at the boundary on the left side, and this is a boundary point on the bottom, which both are assumed to be 0. And this is in the same way we see that u to 0 is a boundary point at the bottom on the right side, which also is 0. This point u3, 1 is this point. Let's see. This point. So instead of writing this, we just put this number into the equation. So now we have 2 equations, but unfortunately we have 3 unknown quantities: u21, u12, and u11. So we need some additional information. What we are doing now is, since we have a Neumann condition on the upper boundary, we do the following trick. We just make a virtual point which does not exist in our problem, but let us just say that, call this point for 1, 3, and this point for 2, 3. And now we can write the difference equation for this point. We can use this general difference equation and write it out for this point and this point. We don't go so much into detail on how this is done, but then we get these 2 equations. On the other hand, we know that the derivative on the top, the partial derivative on, for example, u12 at the top with respect to y is approximately equal to the difference between, let me show you. This we have been proving earlier, that it's approximately equal to the value u in this point minus the value in this point over the length of the distance between these 2 points, which is 2h. And the same, we have that the normal derivative of the partial derivative in this point is approximately equal to the value of u in this point minus the value of u in this point over 2h. So let's just write this. It takes the following form. At the first point we get this, and h is just 1/2. So, and we know that the partial derivative in this point is supposed to be 3. Therefore we get that u13 is equal to u11 plus 3. Why is it 3 here? Let's just explain this for you. We have already said that u and the normal derivative should be equal to 6 point x, and x is in this point equal to 1/2, so therefore we have 3 here. On this point it's twice as much, so it's in fact 1, so therefore it will be 6 in this point. And we get a similar equation for this. We get that 6 is equal to the partial derivative at that point with respect to y, and writing this out in the same manner, we obtain that u23 is equal to u21 plus 6. And inserting these two expressions into these two equations here, we reduce the problem a little bit, and we get 4 equations with 4 unknown, as we now can solve. So we obtain these 4 unknown, and so we have 4 equations with 4 unknown, and it's possible to solve this. We can, for example, invert this matrix, and when we are doing this we find that u12 is equal to this, and it's 0.86. The exact value turns out to be 1. It's possible to find the exact value also in this case. This in parentheses here is just to compare with the exact value. So u11 is 0.77. Well, it's some distance to the exact value here, but it's relatively more close value to the exact in this case, and also in this case. So now we have shown you how we can find numerical solutions in the case of mixed problems and Neumann problems.